G'day, in this video we're going to be looking at Newton's law of gravitation. This video is going to cover the first dot point of inquiry, question 3, which is focused on gravity and how it influences the motion of both planets and satellites. Our key content statement is to apply quantitative and qualitatively Newton's law of universal gravitation. Through application of this law, we're going to be able to unpack the force of gravity between two objects, develop a better understanding of gravitational field strengths and the things that influence them, and with that, account for gravitational field strengths at any point within a given gravitational field. So there are three key learning intentions today. First, we're going to define Newton's law of universal gravitation, and then we're going to apply Newton's third law as well as Newton's second law to the law of universal gravitation so that we can apply this new concept to further context. So first off, let's look at Newton's law of universal gravitation. Effectively, it's reflected in this formula here, which is in your data sheet, that F is equal to G mm on r squared. In other words, the gravitational force on an object is going to be calculated using four different values. First off, we have G, the universal gravitation constant. This constant value allows the other three variables to be related in a formula. Big M is object with mass, capital M, that is exerting a gravitational force on the other object, which we note with the lowercase m. So for example, when before we have done calculations where F is equal to mg, the object's mass that is influenced by gravity is given the little m. Whatever object is causing the gravitational force to occur is given the mass with the uppercase M. Finally, we have r, and r is the distance between these two objects. What's really important to note though is when we talk about the distance between two objects, it needs to be measured from the center of mass of each object. So when we're talking about something like a planet or a star, for example, we need to take into account not just how far the object is away from the star or planet, but also the radius of the star or the planet, as this distance will also make up the value r. So in general terms, the variables which affect the force of gravity between two objects are the distance, how far they are apart. As we start applying this equation, you'll find that objects that are closer together experience a larger gravitational force. As well, it depends on the mass of the two objects. The more massive both objects are, the greater force that exists between them. Both of these concepts, as we start to unpack them further, should follow a lot of qualitative concepts, trends, and observations that we see here in everyday life on Earth, or observations that we see of objects in space. So when we start to apply the concept of universal gravitation to third law, as we know, when a force is applied on an object, an equal and opposite force is applied in return. When we look at gravitational force, there is no exception here. So in our diagram down the bottom, what we have is a force being exerted on the object with little m by the object with big M. And on the other side, we have the force which occurs because of little m that is acting on big M. The magnitude of both of these forces are equal, but we note here in this general equation that the two forces are opposite in polarity, meaning that one force is shown as positive and one force is shown as negative. In terms of universal gravitation and the formula that we just looked at, in any case, when we substitute in values to calculate for the magnitude of force, whether we're looking from the perspective of the object that is lowercase or uppercase m, we're going to be substituting in the same values. We're going to be putting in the masses of both objects, and we are also going to be substituting in the same radius because whether we're looking from the perspective of little m or big M, the distance between the two objects should be the same. While we can use universal gravitation to unpack gravitational forces between two objects, we can go a little bit further and start to talk about gravitational field strength, which is marked as G. Essentially, gravitational field strength describes the gravitational force placed on an object per kilo of mass that it has. This can also be written as force on mass, giving us the unit newtons per kilo. What's interesting to note is how this formula is very similar to Newton's second law, which is that F is equal to ma, which can then also be written as mg. Here in this formula, g is given the units for acceleration, which is meters per second square. Note too that if we rearrange for this formula, we get the same statement as we did for equation 1, and that is that g is equal to F on m, meaning that the gravitational field strength measured in newtons per kilo is reflective of gravitational acceleration as applied to Newton's second law. Note too that when we are looking at these lowercase m's, just as we saw in the formula for universal gravitation, the mass that we substitute into either of these formula, the number that we substitute into either of these formulae is the mass for the object which is experiencing an acceleration. Using this concept of gravitational force, I'm now going to apply it to our formula for universal gravitation, which is going to give us quite a helpful equation. Let's look at a scenario where there are two objects, A and B, exerting gravitational force on each other. In particular, we'll focus on the force that A is applying to B. Here we can say that this force is equal to G, mass of A, mass of B, on R square. And based on our previous work, we also know that the gravitational field caused by A will be equal to the force of A, which is exerting on B, divided by the mass of object B. Combining these two formulae together, we get an expression for the gravitational field of A, which is a little bit more complex. Here in this scenario, the mass of B cancels out, and we find that the gravitational field due to object A is G times the mass of A divided by R square. Another way of thinking about how to come to this formula can be done if we reflect on our F equals ma formula. Again, we know that F is equal to G mm on R square, but that force is also equal to mg. If we look at our first equation on universal gravitation, we can do a slight rewrite and show that it actually follows a very similar form to our F equals mg formula. If I separate my lowercase m and multiply it by the rest of the fraction, we now have two terms, one of which is common. We have two m values that are the same as each other, and we now have a value which is akin to our g value. So what we can conclude is that Gm is equal to capital G, capital M on R squared, just like we showed in the previous example here. What's really important to note is that while this formula is quite helpful, it is not included in your datasheet and will be expected for you to either recall or to quickly derive in a question if required. So now that we have a concept of how to calculate for G, it's important to start focusing on gravitational fields. And these look and behave quite similarly to electric fields that we looked at in Module 4. However, it's important to note that we will always have gravitational fields that go in one direction. And that is because gravitational fields are always an attractive force. So you will not see object M generating a field in a negative direction that moves outward, so to say. Something else to consider is that if you are on a large object like Earth, we can start to assume that gravitational field is uniform at all points on the surface. And that's essentially because the gravitational field will be perpendicular to the surface of the Earth, and if you make a small shift either in any direction from that point, you'll find that the gravitational field is pretty much identical with really no deviance in angle. And that's simply because the surface of the Earth or the circumference of the Earth is so large. In the next slide, I'll show you how we can calculate for the gravitational field on the surface of the Earth based on this assumption. So we know that gravitational field for any object, this one we'll call Earth, is equal to G m on R squared. We know, as always, that G is 6.67 times 10 to the negative 11. The mass of the Earth is something that is given to you in your data sheet, so that's going to be multiplied by 6.0 times 10 to the 24. And the radius of the Earth is also given in the data sheet. Now, the radius of the Earth is not an exact value. There is deviance for this radius, But if we are going to assume that the gravitational field on the surface of a planet is uniform, then we also need to assume that the radius of that planet is uniform as well. So given that, we're going to be substituting the average radius of the Earth, which is 6.371 times 10 to the 6 meters. When we substitute all of that into our calculator, we should get an answer that looks roughly like this. We get 9.86 meters per second squared, and that's to 3 significant figures, which looks quite similar to our acceleration due to gravity, which we apply to calculations in all of our physics contexts. The gravitational field generated by the Earth is not the only object that you'll be expected to calculate for. However, in your data sheet, the mass and radius is only given for the Earth. If you need to do a calculation using any of the formula that we have looked at today, or any other object, you will need to be given these values in order to complete the calculation. However, if the question does focus on Earth specifically, it shouldn't be expected that you are given information on the Earth, but rather you refer to your data sheet to find it. Thank you very much, everyone. In the next video, we're going to focus on circular motion and apply some of these concepts to orbiting objects. But until then, have a good one.